So everybody has their notes out for chapter 11? You ready?
Yes. Ready.
Ready to finish this fast one? Chapter 11 is kind of long. It's got a lot of topics, obviously, but we're going to finish this today and start 12. And 12 is somewhat short. So anyway, so we've gone through all this stuff, where we talked about all the properties of phases, intermolecular forces. We went through all these minor topics. We talked about phase change. Why is phase change important? Because steam burns hurt worse than boiling hot water burns, and you can use steam to clean baby bottles. Okay, that kind of stuff. So we'll talk about how they measure heat of vaporization, and then we'll talk about supercritical fluids. It sounds like if people go to the hospital sometimes in critical condition, what would supercritical be? I don't know, think about it. Okay. But in chemistry, there's supercritical conditions. And then we'll talk about phase diagrams. Okay. So we left off with this exercise, and we did various parts of the heating process. And one part involved the heat of vaporization, and this one was the one where it required the most energy to do that. And that's because we're undoing all of the hydrogen bonding forces and all that stuff. How do they measure it, though, is an interesting question. This would actually make for a cool lab if I had time to put one together and we had room in the lab time to do it. But so how do they measure it? So it turns out that if you graph vapor pressure versus temperature, you get an exponential curve. So vapor pressure increases as temperature increases. That makes sense, right? Heating up something more, or if it goes in the gas phase, therefore the vapor pressure increases. I hope that makes sense. It's sort of pretty straightforward. But it produces a linear curve. And you probably figured this out by now, but scientists, we don't like curves, we like straight lines. It's always nice when you get a linear relationship. Okay, so what happens, this is the equation for vapor pressure as far as these graphs go. All right, and also just something to point out. Notice how like diethyl ether, it vaporizes more quickly versus water, which takes a little while. Okay, so you'll see this play out with the different intermolecular forces of solvents. It turns out that if you graph the log of the vapor pressure versus 1 over the temperature, okay, you get a linear function. We do. Right. So that gives us this equation. They call it the Clausius Clapeyron equation. I might be even pronouncing it wrong, or maybe it's Clapeyron, or I don't know. I've always said Clausius Clapeyron. Okay. So if you graph natural log of vapor pressure, you get a graph it versus 1 over t, you get this linear function. Yeah.
Are we going to have to do something like this on the exam?
Yes, on the exam, I'm going to ask you to get your laptop out or get your phone and do a graph in Excel. No, I'm not going to ask you to do it. No, but they do want you to know it. It's the curriculum. What I could do is I could give you like an actual manual graph, and I could have you just plot it, and estimate it. But it is kind of a nice exercise in Excel, nonetheless. So if you look at this equation, do you see how it could be a straight line? Like y is equal to mx plus b, right? So you get this linear function, right? Y is equal to mx plus b. So the slope is going to be equal to the negative value of the heat of vaporization divided by r, which is the gas constant. Okay, so the r constant, this guy right here, is just the gas constant, but it's units of joule per mole Kelvin. Do you remember using this in another calculation earlier in the semester? Do you remember what you were calculating it? You just remember seeing it, right? This was from root mean square velocity for gases. Right? So we use this version of the gas constant in our slope. And so if you know what the slope is from graphing it, and you know this is a constant, you can solve for the heat of vaporization. So let's just say we have this data. All right, this is just an exercise. It says determine the heat of vaporization for dichloromethane given the vapor pressure versus temperature data below. So they have temperature data And obviously, as the temperature goes up, the vapor pressure goes up. And they graph the Clausius Clapeyron equation. And this is, you might have to do one or two of these in your homework, but this just explains how you would do Excel. So you would type in equals to tell the Excel software, okay, we're going to calculate something. You'd say 1 over the cell number and then press enter for the 1 over t. So you take the Kelvin data in the column next to it, or over here, you could say, equals 1 over, and then click on the cell, and it would enter, and that'd give you 1 over the temperature. And then for the vapor pressure, you would type in equals, and then ln for natural log. So this is how Excel does natural logs. So equals ln, click on the cell number, press enter. And then you click and drag the small black box at the bottom right corner of each cell. Do you remember that as a little black box? You click and just drag, and it calculates them all for you all at once, rather than having to punch each value into a calculator and drive yourself crazy. Okay, so the power of spreadsheet software is wonderful. So if you do that, you would get this data. All right, and then you would graph this in the y-axis, and then this in the x-axis. Okay, and you would get a graph that looks like this. So it's pretty linear. All right, nice r-squared value, close to 1, relatively close to 1. So what are we going to look at when we look at this graph? What are we really honed in on? We're honed in on the equation. This is the slope, all right? And again, the slope is equal to negative delta H vat divided by R. And that's what we would focus on. Okay, so doing that, how do we get delta H vat, right? So we know that the slope, if we look back at the graph again, the slope is negative 3773.5. So basically, the slope is about 3,800 Kelvin. And the R value, of course, is 8.314 joules per mole Kelvin. So the slope is equal to negative delta H vap over R. I always say vap, but I should say vape, probably. Heat of vaporization. So the slope has units of Kelvin. Why is that? So does natural log have any units? No, it's not going to have any units. But if this is 1 over temperature here, that means x is 1 over t. So to make this unitless, you've got to have the units of the slope be Kelvin. Right? So the slope units are Kelvin. And when you multiply it by the x value of 1 over t, it cancels out the Kelvin. Right? To make it unitless. Okay. So slope is equal to about negative 3,800 Kelvin, and then just to do the math here, negative delta H vat, vape, is equal to negative 3,800 Kelvin, and it's divided by, times, right, so we're going to multiply it by R over here, so it's times 8.314 joules over mole Kelvin. And so the Kelvins cancel at that point, and we'll get units of joules per mole. These negatives also cancel each other out on both sides. So it's 3.16 to the 4th joules per mole. But of course, we usually do things in kilojoules per mole. So 31.6, converting joules to kilojoules. So it's not really a hard kind of problem. It's just, you just got to do a little bit of graphing. So I kind of like problems where you have to graph things. It's like, oh, I got to process data, analyze it, make sense of it. Right. So so it takes 31.6 kilojoules to vaporize 1 mole of this dichloromethane. Okay. Any questions about that? Pretty straightforward. You can do it on an exam on your phone. And look up all the answers online.
Yeah, right. Not the way your exams are structured.
It would be kind of hard to
No way.
just look up the answers. Yeah, that would be. All right. Okay, so what if we only had 2 data points? So this is the Clausius Clapeyron equation for a 2-point graph. So it's basically pressure 2 divided by pressure 1. One of these 2 pressures are going to be given to you. There's, if you know what the pressure is at a given temperature, or excuse me, if you know what the vapor pressure is at a given temp, but then you want to know what the vapor pressure is going to be at another temperature, you plug this in here. Okay, so this is less precise than a graph data, but it's still a good estimate. So here's an example. Determine the vapor pressure of water at 25 degrees Celsius. It says your normal boiling point equals 100.0 degrees Celsius. All right, and that's saying that it gives you the vapor pressure, or excuse me, heat of vaporization of 40.7 kilojoules per mole. So what is, going back to this equation, what is our T1 going to be? So the idea is that the normal conditions are considered the initial conditions. And that's an important thing. Let me write that in here. So for normal conditions, the normal boiling point of water is what? 100 degrees Celsius, right? So we'll take that as our T1. Of course, in Kelvin, it's going to be 373.15 Kelvin. What would be the pressure for normal conditions? 1 atmosphere, right? That's like standard conditions. Which is the same as 764. So let's say the second condition now. We'll have our T2 and our T2. So what would be our T2? Yeah, it gives us 25 degrees. And that's the same as 298.15 Kelvin. And then it's asking us, what is the vapor pressure at 25 degrees Celsius? So that's being asked for. So the way to do the 2-point Clausius Clapeyron is to just understand that the normal conditions are the initial conditions, right? And then what comes after is after. And then just to take an inventory of the rest here. So delta H vape is equal to 40.7. And then also the R constant is 8.3. There. So now we have this inventory of variables. And now we're just going to plug and chug. Okay, so to plug this in now, right, here's our Clausius Clapeyron equation. So natural log of delta H vape, all right, divided by R, okay, and it's times 1 over, what is it, T2 minus T1. Just double check this. All right, and so which variable is it asking us for? Which one of these?
P2.
That's for P2, right? So it's saying, okay, what is that? So P2 over P1, plug in just the variables here, 40.7, bless you. It might help us if we convert this to joules, right? So, how do we get from kilojoules to joules again? 1,000. Yeah, 1,000 joules in a kilojoule. All right, so kilojoules cancel, joules cancel. These Kelvin here will cancel out these here. Oh, I left out the moles here. Alright, it's kilojoules per mole, which cancels out this mole per mole here. Right, so kilojoules cancel, everything cancels. That cancels, this cancels, everything cancels. It's all unitless at this point. So if we do, just if we run all these numbers in a calculator, and the way I suggest you do it is take this difference first and then multiply it by this part. You would get something like negative 3.30. So, testing your math knowledge here, how would we solve for P2 from this point? Yeah, take the inverse natural log, right? So you take the e both sides, right, and you'll end up getting P2 over P1 equals e to the negative 3.30. Does anyone remember how to do natural log on your calculator or take the inverse? Yeah. If you don't remember, try it. You know, at some point, you could do it after you want to with the calculator and see if you get the answer. So taking the anti-natural log, okay, you get some value of, let's see, 0.0369, some value like that. And since we're solving for P2, we know that P2 would be equal to 0.0369 times P1. And P1 was equal to what? 760 torr. All right, so and this is the easy part at the end here. So this is coming out to be 28.0 torr. So does that answer make sense? Well, at 100 degrees Celsius, we have a vapor pressure of 760 torr. Okay, at 25 degrees Celsius, it's 28 torr, right? The vapor pressure went down. So at least from that standpoint, the answer makes sense. So there's a little math involved. This could be on an exam, right? You know, graphing not so much, but 2-point variation of it could be. Gotta love math. See, we were doing all these dispersion forces and intermolecular forces. Now it's back to math again. Man, all right. Although I like it, but anyway. Okay. Any questions about Clausius Clapeyron? Ready to do something different a little bit? Let's talk about supercritical fluids. So as a liquid is heated in a sealed chamber, the vapor pressure will increase. That makes sense. The density of the vapor will increase, and the density of the liquid will decrease. Man, I'm not even talking right today. So you're heating up this liquid, right, in a chamber. Right, you got this liquid, and you're heating it up. Okay, and then you take the same chamber, roughly the same volume. Okay, and then you take the very same chamber, okay, and the vapor, so you're heating this up, right? The liquid level is actually expanding as well. Alright, so density of the liquid, the liquid expands, its density is decreasing, but the vapor pressure above is getting more dense. Alright, and so this is what happens is you heat a liquid in a sealed chamber. At some temperature, if it gets hot enough, and if the vapor pressure increases enough, the meniscus between the liquid and vapor phase starts to disappear and commingle, all right, and form what we call a supercritical fluid. All right, so here's a picture of it. Okay, so here's liquid, gas, all right, continue to heat it up. All right, notice how the liquid level is staying the same, okay, but it's getting less dense, right? There's actually less particles. The other particles left the building and went up here, all right? And then as you keep heating it, the pressure is getting really high, but the temperature is also getting really hot, okay? And so you get this mesh called the supercritical fluid, all right? This is where the liquid phase, vapor phase, and solid phase all converge, okay? All right, and it starts to become this, sort of, gas and liquid together. Okay, so we call it supercritical fluid. Kind of interesting. All right, so these are under really extreme conditions for supercritical fluids. The critical point takes place at a critical temperature. Okay, so the temperature required to produce a supercritical fluid is called the critical temperature. The pressure at which the critical temperature occurs is called the critical pressure. Right? At or above the critical temperature, the gas cannot be condensed into a liquid no matter how high the pressure goes. So in other words, you would think, okay, if you increase the pressure enough, it'll force the gas back into liquid. Okay, but it doesn't take place. So let's talk about phase diagrams and kind of visualize this better. Phase diagrams illustrate different states and state changes that occur at various temperatures and pressures. Regions represent states of matter. So when you look at a phase diagram, it's going to be split into solid, liquid, and gas regions. Right? Every phase diagram will have three main regions. Lines represent state changes. There's a liquid-gas line. That's the vapor pressure curve. And along that line, both the gas and liquid are simultaneously coexisting. The critical point is the furthest point on the vapor pressure curve. Right? It's going to be really hot and really high pressure. There's something called a triple point. Okay, and this is the temperature and pressure condition where all three states simultaneously exist. I think I said the critical point is where all these states exist. I'm wrong. It's the triple point. I'm getting the two mixed up. Okay, so the critical point is when you have this liquid gaseous substance. Okay, it behaves like a liquid, but it also can move like a gas. And there's an application of this I'll mention in a little bit here. So for most substances, the freezing point will increase as the pressure increases, right? Because if you're increasing the pressure, okay, you're making it hotter, the freezing point will have to I'm sorry, if you're increasing the vapor pressure, the particles, there's a lot of particles, they start to want to condense, right? So things will start to freeze at a higher temp. Oops. All right, so here's a phase diagram. So here's the interface between solid and gas. What process do you think would occur going from here to here? Okay, this is like a sublimation. So this line right here represents given temperatures and given pressures. So from here on down, and from temperatures on down, anything in that region you can have sublimation. All right, and then if you keep going up now, you can go solid melts into liquid, right? So this is the fusion line, and then liquid to gas. This is the vaporization line. So you remember when we looked at vapor pressure curves, they kind of all went up like this. You know, this is a few slides back. So this is the vapor pressure curve, right? Vaporization, condensation. That's the fusion curve. Sounds like a good brand name for something. Fusion curve. There's the sublimation curve. And the critical point is way up here. All right, so at that point, vapor and liquid converge into this mix that's sort of gaseous, but also kind of behaves like a liquid. And then this is the triple point. This guy right here. So the triple point may occur at a really low temperature and also a really low pressure. You know, things are getting cold. And the critical point, the triple point, these things will shift depending on what substance it is. So each substance